Ever my Memorex. That's an old one, but a good one. All right, it is Friday, and I don't know if I'm live. I'm just going to assume I am. Welcome. Happy New Year. Happy New Year. Happy New Year. Happy New Year. Welcome to another Q&A Friday. Here on the Technical Social Distancing Network, seems like everybody's getting back down in their basements again due to the whole COVID stuff and this new strain. But that doesn't mean we can't learn something and communicate some way. So hopefully I'm live. I don't know if I am or not, but it is what it is. Okay, so let's talk a little bit about some questions that came in. Remember, this is a session. This is Friday. Happy New Year, Hassam. Where are you located, Hassam? Where are you at? Man, you look familiar. Anyway, I'm streaming all seven platforms. If you don't remember, if you haven't been watching, I am on my YouTube channel. It's going to be YouTube only. I'm walking through NEC 2023 code changes. I'm trying to develop my slide deck. So I'm going through a process of selecting which ones are significant changes, which ones aren't, and I decided to do it live on my channel. So and we had a great discussion yesterday. So I did 2 sessions yesterday. I did a 12. Happy New Year's. San Francisco, awesome. Hopefully it's nice out there in San Francisco. You know what? There's a restaurant in San Francisco that I absolutely love, and I think they're closed now. Francino's, Italian. I believe Mr. Francino passed away, and I think they closed. But every time I went through San Francisco, I always went to Francino's. Walk up through through Chinatown, and then you make the left and another left. Anyway. I divert. So I'm working on at lunchtime yesterday, and then at 5 o'clock yesterday. In fact, I went 2 hours. I only wanted to do 1 hour sessions, but I actually went a little bit longer than I wanted to. But we've worked through Article 90, and we're in Article 110 right now, and there are some interesting changes that are coming down the pike. So what I'm trying to do now is I'm trying to pull together which portions of my 2020 slide deck that I need to. Hey, William Snyder. Yeah, it was an interesting discussion yesterday. I really enjoyed it, and so what I'm doing is I'm just trying to you're going through the process of trying to figure out what is important to teach on, to bring the awareness of electrical contractors, electricians, installers, even manufacturers. What's going to impact our products, and what impacts our customers impacts us as well. How do we make life easier? So I'm doing that, and I'm doing it live. And I don't know how it was going to go, Mr. Snyder, but I think it was fun. I know I had a good time. And you know what? If somebody wants to sit down and watch us have a good time, grab a cup of coffee and enjoy. But today is Q&A Friday, and I did not want to miss this one. So I had a couple questions. One of them is how I'm doing this, but I'm going to cover that at the tail end of this if I have some time, because I keep getting questions they ask me about my studio. How do you have it set up? What do you use? And all this other good stuff. So I might talk a little bit about that at the end. But first question that came up was, this question was Lsig. If you recall, I think it's on the IAEI, don't forget, IAEI Tuesdays at 12, IAEI News Live. What I'm doing there is I'm doing TCC curves, time current characteristic curves. And we have a little sample one-line system that I'm doing in SKM. And next Tuesday, which I got to create the little thing for, but next Tuesday, we're going to continue that discussion. That'll be part 3. And we are going to talk about what we've developed so far in that is we have I think a 2,000 amp main service panel. I talked about the overcurrent protective devices on the primary and secondary of a transformer. We talked about the transformer damage curve. Well, and I'm going over the trip curves to show how we provide protection. So on that IAEI channel, it's IAEI News Live, so you're going to want to tune into that one. We're going to continue that discussion. Well, this question, I believe, came in because of that, because it says he was watching the TCC lesson today. He says he noticed I mentioned that a 2,000 amp switchboard needs LSIG. Now, it was the 2,000 amp switchboard that was in my program. Okay, and I think what David might be misconstruing or forgetting is that 2,000 amp switchboard was service entrance equipment. So he says, I noticed you mentioned that the 2,000 amp switchboard needs an LSIG, which being groundfall. It doesn't need long time, short time, and instantaneous. The LSI, it needs groundfall. But he says, I have a 1,200 amp, 480 volt, 3-phase, 3-wire, 60 hertz, 65 kA motor control center that is fed from a 1,600 amp feeder breaker in a switchboard. The switchboard is outside and the MCC is in a building. The switchboard feeder breaker has LSIG, but the MCC does not. Does the MCC main breaker need to have LSIG? So first on that question, so if the LSIG, believe me, I have a code book. And believe me, there it is. My code book was moved, so bear with me. I'm going to use my feet to get it. All right. Lou, thanks for joining. Just got in from removing snow. Yeah, we got snow too outside. And you know what, Lou? You can come on over. My driveway needs plowed, so I'm waiting for you. Bobby Joe will make some hot cocoa for you. And then after you have your hot cocoa, you can come down here and I can get you some Ardbeg or some Lafroig triple wood. That would be very nice and warm you up a little bit. So in this discussion on, remember, groundfall protection of equipment, there are various areas in the NEC that deal with requiring groundfall protection of equipment. Article 230, which is service entrance equipment. Then you have Article 215. Now, the key thing to remember in Article 215, which is for feeders, what they'll tell you is that a feeder should have GFPE unless, and there's an unless associated with it. So groundfall protection of equipment, it says each feeder rated 1,000 amps or more and installed in a solidly grounded Y electrical system of more than 150 volts to ground, but not exceeding 600 volts phase to phase, shall be provided with groundfall protection of equipment in accordance with 23095. There's an exception though. Exception number 1, it says this section shall not apply to a disconnecting means for a continuous industrial process where a non-orderly shutdown will introduce additional or increased hazards, because you got to remember, GFPE looks downstream. Exception number 2, this section shall not apply if groundfall protection of equipment is provided on the supply side of the feeder and on the load side of any transformer supplying the feeder. So that's the one. So he said that he has a 1,200 amp motor control center fed from a 1,600 amp circuit breaker in a switchboard. He says that the 1,600 amp circuit breaker has LSIG, but the 1,200 amp, the switchboard feeder breaker has LSIG, but the MCC does not. The switchboard feeder breaker, 1,600 amp feeder breaker, is fed from a 1,600 amp feeder breaker. So the feeder breaker has GFPE, but the MCC does not. That's okay. Just because you have a 1,200 amp motor control center, and maybe you have a 1,200 amp breaker in that motor control center, doesn't mean you need GFPE, because it can be supplied from an upstream overcurrent protective device. If it's upstream, then remember, groundfall protection of equipment looks downstream, and that is a plus and a minus for ground fault protection of equipment. What is the challenge when we think about ground fault protection of equipment? When I just think if I told you in your residential home, instead of putting GFCI receptacles or GFCI circuit breakers on every circuit, just put GFCI on your main. You'd probably go, what? Right? Because you don't want to take the main out for a ground fault on, in the bathroom, because you want to be watching the football game and you don't want a problem in the bathroom to interrupt your football game. You want just the bathroom to go out. Well, that's the problem with putting GFPE at service entrance equipment. Yes, it's at maximum setting of 1200 amps and whatnot, but think about it. You have all of this equipment downstream that if you put GFPE downstream on the branch circuits for a fault on a branch circuit, how many people were on 277 volt lighting had a problem and took the main out, right? Because you had a ground fault on 277 volts. The big hoppy said, hey, Michael Savage, Happy New Year, brother. Good to see you. Good to see you online. So the challenge with ground fault protection of equipment at the service entrance equipment is that it looks downstream. But for this question, you don't need to put GFPE at the MCC because you're covered from that upstream device. Just because your breaker is 1200 amps, you have a 1600 amp breaker upstream that has ground fault protection of equipment. You don't need it downstream. The reason I said on that IAEI program that you needed GFPE on the 2000 amp was because it was service entrance overcurrent protective device. And per Article 230, that device, if 1000 amps or more, has to have ground fault protection of equipment. When you go to feeders and branch circuits, there's an exception in there that says if it's upstream provided, you don't need to provide it. But I'll tell you why you want to provide it. It's not because the code requires it. It's because when you have a problem in the power distribution system, you want to take only a portion of the power system out, not the entire power system. So the advantage, and in my opinion, if I was doing 277 volt lighting, I'd put GFPE on those branch circuits that fed that lighting. Because if I have a ground fault on that lighting, then I want that branch circuit to be taken out, not my service entrance. Now, if I'm going through a delta Y ground transformer, I don't have to think about ground fault downstream on the secondary of the transformer side, because ground fault currents will not pass through a delta. So if I want to isolate my system, I can do a couple things. If I wanted to reduce the likelihood of taking out my main because I have a ground fault somewhere down further in my system, I've got a couple options on the table. One, I can put a delta Y ground transformer. So a ground fault on the secondary of that transformer won't pass through the delta on the primary, circulates in the delta. What does a ground fault on the secondary of a delta Y ground transformer look like on the primary? It looks like a phase-to-phase fault. So you'll have higher currents in phase-to-phase, but you won't let a zero sequence CT upstream pick up on that. And so can I call you Bill or do I call you William? Let me know. I'm going to call you Bill, but if you want me to call you William, I'll call you William. I'll call you William unless you want me to call you Bill. So William, coordination. So when I have ground fault, I need to think two things. I have to think about my ground fault currents. When I'm evaluating the response of a GFPE device, I don't coordinate to the three-phase bolted fault because it's a three-phase bolted fault. Hey, Nihad, good to see you. Yeah, we're getting back into the time, the whole no travel in the basement stuff. So anyway, I don't have to coordinate to a three-phase bolted fault because it's a three-phase bolted fault, right? And a zero sequence CT or ground fault, phase to phase to phase is not ground fault currents. There's no zero sequence currents flowing. It's all positive sequence currents. Now, if you're not a symmetrical component guy, then you don't know what the heck I just said. But if you are a power systems engineer, you understand symmetrical components from Mr. Fortescue back in the day who created it, then you'll understand what I mean by zero sequence or positive sequence or negative sequence. So, but when you have a three-phase bolted fault, that is a positive sequence current, no zero sequence, no negative sequence. Your zero sequence CTs, your ground fault protection, will respond to zero sequence currents. They won't be flowing on a bolted fault. So they will be flowing on a line to ground fault. So what we do, Mr. Steve Froming, he may be late, but he's worth the wait. What we do for zero sequence, when we coordinate things, we've got to look at the ground fault currents that are going to be flowing. And we have to consider, now those are going to be lower, but we have to do a evaluation of our time current characteristic curves with regard to the standard curve of the downstream overcurrent protective devices and the upstream hockey stick curve from GFPE. Why? Because a line to ground fault will be a single phase fault where will be current flowing through one of the phases feeding the ground fault. Or if it's a double line to ground fault, two phases feeding the ground fault. That is real current. It's not a zero sequence current to that downstream device. That is real current flowing through one phase or two phases or three phases. Doesn't matter. It's still an overcurrent, but it's going to ground. So that standard trip curve will respond to that ground fault current. And you have to make sure that that trip curve is to the left of the upstream hockey stick ground fault current, ground fault trip curve. So you still have to consider the TCC curve, standard TCC curve. It will be a lower current. I think it was, I'm not sure it was Bill. Yeah, Bill. It will be a lower current because it'll be your ground fault currents, but you'll have to do an evaluation of the standard TCC curve for the downstream device and the upstream hockey stick, which is your ground fault curve. So that evaluation still has to happen. And I would still say, is that selective coordination? Selective coordination is all currents, all times. So yeah, it's still selective coordination for ground fault conditions inside of a power distribution system. But again, if I am going through a delta Y ground transformer, the secondary breakers will see the ground fault. The primary will not. That's one way to isolate your system a little bit. Oh, Willie Snyder. Okay, Willie. I you know what? I like Willie because I'm a Willie Nelson fan. So Willie Snyder. So the other way to isolate. What is the other way? I can put a the other way to make sure that I have I don't take out the entire facility is if I put ground fault protection of equipment down further in my system. So if I put GFPE on my lighting circuits, because remember, if I'm at 480 volts, the moment I go down to 208, I'm going through a delta Y ground transformer. I'm no longer have ground fault. A ground fault down on the secondary won't impact that. So it's at 480. It's the 277 lighting that you would be seeing this on. I would put GFPE or on those motors. He has an MCC. 480 volt MCC, 1200 amp MCC. Would I put GFPE on there? I probably would. I'd say you don't have to, but I probably would and try to get it to coordinate with the ground fault protection that's on that 1600 amp breaker so that I have my two hockey sticks. Yeah, this is how you would see it, right? I have, say this is my upstream and this is my downstream. Right? So it's something like that. That's how it would look. I'd have two hockey sticks nested so that the 1200 amp ground fault protection would clear first before the 1600 amp ground fault protection. Now I have coordination. So if I have a problem in any one of those motors or in that MCC, that main overcurrent device will open and not take out the main. So it's not an NEC requirement unless you have, remember, you need two layers if you're of an Article 517. Right, Willie? If I go to Article 517, there's a requirement for the life safety, and I'm not like some of you guys who can just you can just come up with section numbers off the top of your head. Oh, here, look at this, 517.17, where groundfall protection. I came up with this right off the top of my head. I don't know why you can't. Where groundfall protection of equipment is provided for operation of the service disconnecting means or feeder disconnecting means specified in 230.95 or 215.10, an additional step of groundfall protection shall be provided in all next level feeder disconnecting means downstream toward the load. Why do they do that? They want to coordinate, and then there's a requirement that they be selective. They selectively coordinate the GFPE devices. Why is that? Because they don't want to take the main out when they can just take one feeder out. Well, I could go as far down in my power distribution system as I can to isolate my problem and not take out the main. I think it's a good practice. I think you're doing your service. You're doing a good service to your customer, your client. Even if it's an office building, I know that I know that some people probably would feel better if I don't have a working computer in front of me and I work less and not more. But you want to keep as much of your facility up and running when a fault occurs somewhere else in the system. Don't take things down needlessly. It improves efficiencies. It improves. It could impact the bottom line, especially if it's a manufacturing facility. So, but I would say is I would consult my customer and say, look, here's why I'm recommending it. Here's how much it's going to cost. I can do this, which will be X amount of dollars. I can do this, which will be X plus Y amount of dollars. And here's why you might want to choose this. If it's a manufacturing facility, if it's a, data, well, I'm going to say data centers, but if it's an application that could benefit from it, I think it's something I would recommend. And if and you don't want to lose an order because you're going to add some cost, I would put that as an option and talk to the owner and see if you can't get them to buy in on it. But so to answer David's question, I said the 2000 amp device had to have ground fault. And because it wasn't a service over current protected device. Feeders don't necessarily have to have it per the code, but you could put them in for additional reliability. Man. All right, so that's that question. Willie wants to talk about laundry areas. What's the debate? Are you talking about the laundry, what do they call it? The not the basin. If you look at the definition of laundry areas, I'm not sure really if you want to talk about if you want to get into this whole discussion of what a, oh my gosh, I can't even find it now. There's a definition of a laundry area. Designed to contain a laundry tray. Oh yeah, a laundry tray, or do you call it a tub? So here's, all right, this is what we're going to do. We really want to do this. We're going to do this. So I'm going to go to Webster. I'm going to go to Merriam, whatever her name is, Webster. I need my keyboard. And we're going to go to Webster. Oh, look at this. It's in my memory. Webster Dictionary laundry tray. So laundry tray definition. What does Merriam-Webster tell us? A fixed tub as of slate, earthenware, soapstone, enameled iron or porcelain with running water and drain pipe for washing clothes and other household linens. So here's the problem if you just call it a laundry tub. If it's a laundry tub and it doesn't have running water in it, you would still have to provide GFPE. The laundry tray adds more. Oh man, how do I get rid of that? X. The laundry tray adds other dynamics to it. It says it has to have running water to it. It has to have a drain pipe. And, washing clothes or washing household linens, I don't care what you wash in a laundry tray. But it's a defined term. The variant is a laundry tub. So we had this debate on panel 2. And quite frankly, I didn't care. I don't care if you call it a laundry tub or if you call it a laundry tray. I think the industry will know what we're talking about. But I'm just telling you what the debate was. And the argument was it is a defined term in Merriam-Webster. If anybody wanted to say, what is a laundry tray? You go to Webster's dictionary and look it up. And it says it's a fixed tub. It could be of slate, earthenware, soapstone. So if I do a laundry, let's do laundry tub. Laundry tub takes you to laundry tray, and it tells you the same thing. If I just said tub, a tub is a small round container in which a product is sold. A wide, low vessel originally formed with wooden staves, round bottom, and hoops. So if you have a tub, a GFCI within 6 foot of any tub wouldn't make sense because I think people would say that's kind of expanding. So this is where the discussion was. And what panel 2 ended up doing was saying, look, we're not going to change it. We're just going to leave laundry tray there. It is what it is. If you want to know the definition of it, go to Webster. Now, we can have a debate on, remember what the style manual says, not the style manual, where I think the area of measurement of that area has been debated too. So the other question that came into play with laundry was, what is a laundry? Right? Laundry area. So the other debate we had on panel 2, and I don't speak on behalf of panel 2. I don't speak on behalf of Eaton, NFPA, on anybody. What you hear come out of here, it's coming from the heart, and it's me. It's just my opinion. Take that for what it's worth. So we had this discussion on panel 2 because what happened was we came out with laundry area for GFCI protection. And I have a theory, Willie, that the reason we have expanded definitions is because we have GFCI requirements. The moment you say, boy, you know what, you have to have GFCI protection for receptacles in a laundry area, people go, well, what's a laundry area? That's not a laundry area. Well, you got a washing machine and a dryer. How's it not a laundry area? Oh, no, that's a closet that happens to have a washer and dryer in it. And it's kind of a big closet. So all of a sudden we don't know what a laundry area is. We have a requirement for GFCI protection in a crawl space. Whoa, what's a crawl space? We need a definition of a crawl space. You know what my opinion is? GFCI protect everything. And now we don't need definitions. If we had GFCI protection on every circuit inside of a house, you wouldn't need to know what a kitchen would be. You wouldn't need to know what a laundry is. You wouldn't need to know what a garage is. You wouldn't need to know what a crawl space is. You wouldn't even know what a bathroom is. We could make life so much simpler if we just said, just GFCI protect everything. I mean, GFCI protection, people get killed from electricity, not because they're near water, not because they're near a hose or near a basin. They get electrocuted. And we saw this in the CPSC data. We did some expansion in 2023 for appliances. And you say, well, is the appliance within 6 feet of a sink? No. Does it need to be within 6 feet of a sink for me to get killed on it? No. I don't even have to have water in it. People were getting killed on microwaves because they were working on the microwave. the electrical worker. Now, we can make an argument and say, well, wait a second. That is an electrical worker working on an appliance and he got electrocuted. That doesn't mean you need GFCI protection. We put GFCI protection in for electrical workers. You go to 210.8, and I love having this debate because, it's one way. I can't hear you. If you go to 210.8D, E, equipment requiring servicing. So in 210.63, we have a requirement that says you need to have a receptacle for equipment that requires servicing. Why? Because you're going to have a maintenance person there troubleshooting, doing servicing. And if that person is plugging into a receptacle, they deserve, the electrical workers' lives work better too. So they need shock protection. So we're saying we need to make sure that the electrical worker is protected. We're going to GFCI protect that. But here we are looking at appliances in 210.8, and we know a lot of the fatalities that we saw, especially on microwaves, is because of people working on the microwave. Are we saying that the person who's working on the microwave, the electrical worker, doesn't deserve GFCI protection? I would hope we're not saying that. Now, I could take the microwave out and work on it, plug it in the dining room. I could take it over to the dining room and plug into the wall. Well, there's a reason to say, well, maybe I need GFCI protection for other circuits in the home. So that's where my head's at. If you go to the CPSC database, you'll find people die in their bed because they're using those electric warmers and they failed. We have people dying in their chair that is electrical. It's plugged into a wall because it lifts them out. And it's a moving piece of equipment, and it failed, energized the chair, and the individual elderly was electrocuted and killed. So we have instances of that. But the moment we start talking about expansion of GFCI beyond something within 6 foot of a sink, everybody's hair goes up on the back of their neck. And then they look at me and say, well, you make those and you sell them. That's why you're promoting it. No, I'm just looking at the freaking statistics. And what we did on panel 2 in this regard lines up with the data, unfortunately. People say we need substantiation to expand GFCI. Well, substantiation is in the Consumer Product Safety Commission database, and that's only a portion of the deaths. And you're looking for a body count. How many bodies does it take? I don't know. I don't know the answer to that, and I don't want to come up with an answer. But that's basically what we're asking for. So anyway, laundry. So the laundry tray is still a debatable item. Does it go to laundry tub? It could. I need public inputs. I really don't care. Either way, I think we'll know what it is when we see it. But I look when I sit at panel 2. Personally, I represent NEMA on code making panel 2, and quite frankly, I look at the NECA, the independent electrical contractor guy, and the electrical inspector. And I go, what do you guys want to do? What does IBEW want to do? What does the IAEI want to do? They're the ones who are going to be living with it and go for it. 210.8F, yes, outdoor outlets was multiple deaths. Actually, Willie, if you look at the Consumer Product Safety Commission, what drove that was my buddy Nihad. Nihad found that, and yes, Daniel, I will address that too. Just given the example, it would be great if you could rework that example. If no X to R was given, let's. I'll talk about that in a second. What time is it? 12:34. I might have some time to just touch on that one. So Nihad brought up the 210.8F and raised the awareness of the death of a child who jumped the fence, put his hand on the air conditioning unit, and was killed. Subsequent to that, when you start looking into it, you find other examples of deaths on these outdoor HVAC equipment from touching the equipment. We also find deaths of individuals who are working on and troubleshooting those HVAC equipment. And remember, troubleshooting is justified energized work. I agree with you, Nihad. It is very frustrating that you have to justify the expansion of this, but it unfortunately it gets so much scrutiny. And you know, all of my circuits in my house are GFCI protected. Every single one of them. Anybody who comes to my house, their life is too important for me. I don't want to lose anybody in my home to a shock due to any reason. I don't care if it's a person, if it's my maintenance person who's working on my stove or working on my dishwasher or my washer or dryer. Every circuit is GFCI protected. Go away, leave me alone. That's my philosophy. It's not. I can't make it a code requirement unless we get 2/3 on code panel 2. But that's where my head's at. So nobody should die in their home from the use of electricity, period. There's no reason for it. And the technology is not that expensive. So, but anyway, beyond that, Mr. Moreno had a question on wondering how you got the Z per unit of 0.0083. And this was my infinite bus calculation. So now remember what is infinite bus, gentlemen and ladies? An infinite bus calculation is you've got to think about the circuit. Infinite bus. I'm just going to do a quick search for infinite bus. You've got to think about when you're modeling a circuit, anytime you're going to calculate short circuit currents, the first step is to create an impedance diagram. Well, the first step is to have a one-line diagram. The second step is, I got 4 files. Let me try this one. All right. I'm going to minimize this. I'm going to minimize this. First step is to get a so the first step is to get a one-line diagram like I got here. The second step is to create an impedance diagram. So what you do when you're doing a short circuit study, you have to convert all of the components of impedance into a real and reactive. If you really want to get close to if you want to, get down to the details, you want to get a real and reactive component to the impedance. In some cases, we'll just assume a reactive component. Now, when a utility gives us data, like for available fault currents, they'll typically give us an X to R ratio. Or if I have a transformer, I can typically find, depending upon the size, I can get it from the manufacturer of the transformer that tells me the X to R, or I can go to IEEE standards and get a X to R ratio. So Daniel, you said a Z per unit of 0.0083. I'm going to find 0.0083 if it's in here. I'm not sure what version. There it is. Okay. All right. It's the utility per unit. And I'll tell you where I get that from. I have to go under the covers. My library is behind the covers. Oh, you can't see it. Industrial Power Systems Handbook by Donald Beeman, first edition, McGraw-Hill, 1955. The equations. These guys are going to dialogue in here about groundfall protection, but Dan, I am bound and determined to tell you how I came up with 0.0083 if no X to R was provided. So 0.0083. Okay, I need my calculator. I use an HP. Are you a TI person or an HP person? So in this book, what I like about this book is there is one page that has a list of equations on how to calculate the per unit impedance of the utility provided information, depending upon what they're given. So if you have a first edition Beeman handbook and you go to page, oh my gosh, there's equivalent circuits. Man, I could never find this. Here it is. Per unit ohms. So and I did this based on per unit. So I'm trying to find. There's the base representing the utility supply system. Okay, so where are my equations? If given short circuit amperes, convert to a percent by equation 1.7. Where 1.7 I think is up front. 1.7. There's one nice page that has, yeah, here it is. Okay, so on page 38, and there's your equation 1.7. So here is what they do, and they give you a percent reactance if the utility gives you short circuit amps, you have to convert it to per unit ohms, and the percent reactance is equal to the kVA base. So boom, 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 kVA base. So let's do this. I am going to insert equation. Okay, so I think the question comes from the fact that it was 0.0104 in the previous slide, and then the value is 0.0083. Utilities, there's the utility Z per unit, so I don't have to do the math. I see what you're saying. .0104 per unit. This is where the power of the unit comes from. Based on this equation, impedance of 0.0104. All right, so we get 0.0104. I had to have assumed a .0083. I see what you're saying. Okay. All right. So okay, you know what? And I'd have to, why did I do the .0083? I got to remember where, and I didn't document it. I don't know why. Usually I'm pretty good at documenting. I went to .0083, but see, I have an angle of 90. So Dan, that's why I'm thinking that I did not include the X to R ratio, because if I had an X to R ratio, then if I had an X to R ratio, that angle of 90 would not be angle of 90, because the X to R ratio would have been a different angle. So you know what I think I will do? I can do that now. So if it was where is it at? I'm gonna do a file, save as. Infinite bus correction. I don't know what folder it's in, but I'm just going to make a modification. So, boom, 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 boom. So infinite bus, 1245. I got 15 minutes, so we're gonna play with this a little bit. I got 20,000 amps of available fault current. I have a 1500 kVA transformer. I don't have an X to R ratio from the utility. I've got 5.75% impedance. I have a fault current I need to calculate right here. I'm not including the conductors, just the utility and the transformer. So I have to convert this into an impedance diagram. I know that my 5.75%, now sometimes the transformer manufacturer could give me an X to R ratio. I'm going to assume it's all reactive. To get it to per unit, I take 5.75, divide that by 100, and I get 0.0575 per unit. So that's this portion of the impedance diagram. Now I've got to convert 20,000 amps to my Thevenin equivalent per unit value. And I use the Beeman handbook, kVA base over I short circuit. Let's just make sure I did the equation. So 1500. You know, I got glasses to see up close, and I'm looking over them. So 1500 divided by 20,000. Divide that by the square root of 3. And then divide that by the kV base, which is 4.16. I get 0.0104, so that number's good. So that is the utility per unit impedance is 0.0104. And then what I did here was I showed that as the fault current goes up and approaches infinity, because it's in the denominator, my utility my impedance goes down and approaches 0. So as fault current approaches infinity, my impedance approaches 0. Hence the infinite bus, right? So that's what I'm saying there. So now I'm back to this, right? As the utility available short circuit current increases to infinity, this is okay. So I'm hammering that point home. So that helps you understand the infinite bus. So now I go straight to this. So let's change this to 0.0104, 0.0104 at an angle of 90. So 0.0104 at an angle of 90. So V Thevenin, I short circuit, .0104, 0.0575. What was it before? Okay. All right, so 0.0104. So that bottom number, 0.0104 plus 0.0575, and I can add both of these because they're both at an angle of 90. If they were at two different angles, I would have to do things a little bit differently. So it's 0.0679 at an angle of 90. So my I short circuit is 1 over, which is 14.7275 times 1804, which is 26,000.57. Actually, I'm going to do 0.6. 26.6 kiloamps, right? 26,568 amps. So it's 26.6 kiloamps at an angle of negative 90. Hopefully that makes sense. So what I've done is I've taken 0.0104 plus 0.0575. Because they're both at the same angle, I can just simply add them. If I had the X to R in both of these, I'd have to do complex. I'd have to break it down into real and reactive, add the reals, add the reactives, and then do the angle. So because this is 0 plus J 0.0104 plus 0 plus 0.575, J 0.575. So if you know complex variables, you know what I just said. So that's how I would add those two. Yeah, 1804 is I base, right? Because that's the full load amps, and it's on the secondary of this transformer. So my I base is based, because my fault current that I want to calculate is on the secondary. My I base is going to be on that secondary. Because it's per unit, I would, remember, I add the impedances up, and then I have to calculate my fault current, which is the per unit current times the base current at the location where I'm going to do the, I want to know my fault current. So, which would be right there on the secondary, and that's why 1804 is my base. 0104. 0104. And so this, what this shows you is, if I, and I think the way this works, let me just do presentation mode, right? So what I'm saying here is, there's my available fault current, and that's my 0.0104 plus my 0.0575. My I base is 1804. I get 26,600 amps. That's when I include the utility. But if the utility's fault current is going to infinity, the impedance is going to 0. So my 0.0104 goes away because 0 impedance. And now my available fault current is based purely on the impedance of the transformer, which is 0.0575 and 31,370 kiloamps. I got to fix that too. Kiloamps is my infinite bus calculation. So if I, and a lot of people say, you know, I'll say, my infinite bus calculation came out to 31,370 amps. And they say, okay, I say, now I have a utility, and and the utility is going to give me 200,000 amps of available fault current. What happens to my 31,370? Does it go up or down? And they'll say, well, you have a utility, 200,000 amps, it's going to go up. It's going to be more than 31,000 amps. And I'm going to go, no, it's not, because it's going to go down. And why? Because I assumed an infinite bus, which means the utility impedance is 0. Anytime I add any fault current, it will go down from the utility. So the worst case scenario is going to be my infinite bus calculation. And we could do the 200,000 amps. 200,000 amps would be easy, right? So my utility impedance would be 1,500 divided by 200,000. Divide that by square root of 3. And divide that by my kV base, which is 4.16. So 0.001 is my impedance. So if I take 0.001 plus 0.0575, and I do 1 over that, multiply that by 1804, I get 30,816. My infinite bus calculation was 31,370. So for 200,000 amps of fault current from the utility on the primary of this 1500 kVA transformer, my fault current goes to 30,816 amps. The infinite bus calculation is 31,370. So anytime you are giving an available fault current at the primary of the transformer, your infinite bus calculation will always be greater. And 1804 is the base because it's at the secondary of that transformer is where that's my base current for everywhere on the secondary of that transformer, because that's the secondary full load amps. If I wanted to know on the primary of the transformer, or if I had, so if I had another transformer a few layers down, so say I was going through another secondary transformer, I could add all of these per unit impedances together, and then I calculate my short circuit current, and to get it back to actual amps, I multiply per unit by the base wherever it is in my power distribution system. So if I was on the secondary of another transformer downstream, the full load amps on the secondary of that transformer would be my new I base, and then I would calculate my per unit times that base to get the fault current at that area in the power system. And that's the rules of per unit, based upon Fortescue, who came up with that. That was an IEEE paper. You can still find it. If you're an IEEE member, you can go up on the IAS, search for CL Fortescue. It was probably back in the 1800s. I don't know what year. I have a copy of it. So that is a good catch, Daniel Marino. Thank you for that catch. And that got us to 1256. Perfect. Man. So here's what I'm going to do. I'm going to redo that presentation. I will redo that one. I need to put that on my action item list. And I can't find my pen. I need my Keith. I need my, oh boy. I lost my, oh boy. Anyway, I'll find it. It's around here somewhere. Okay, so that takes care of your question, hopefully. Thanks for bringing it up. That took care of David's question. I had one other one. So here's the other one, and I don't know if I answered this one before or not. Surge. So I have a panel board. I have a panel board with a surge inside the panel board. And the electrical inspector flags it and says, hey, is this right? Because the overcurrent protective device that was providing that was being used, that the surge protective device was wired into, was not protruding through the, oh, Dan, you're taking your PE test. Oh, excellent, excellent. I'll tell you what, if you're taking your PE test, you know what I'll do is I've got my bookcase. I got to do some stuff tonight here anyway. Over the weekend, I will give you some references that I used when I was studying for my PE exam. I did a lot of questions and problems. I found some really good, a couple good books that had sample problems in them. Doing those sample problems is a really good way to study. At least that's how it helped me. So I did some of that. I'd love to get a program together to help people get their PE. It's sort of a dream of mine. So anyway, the question: if I have a panel board that has a surge protective device inside, supplied through a circuit breaker, where the circuit breaker is not accessible through the dead front, is that legal or not? I'll tell you, it's listed equipment. So a couple things from an inspection perspective. 110. And we talked about this a little bit during my code change stuff. 90, Article 90, Article 90, Article 90 in the enforcement. Nope, not enforcement. Examination. It is in the intent of this code that factory installed internal wiring or the construction of equipment need not be inspected at the time of installation of the equipment, except to detect alterations or damage if the equipment has been listed by a qualified electrical testing laboratory that is recognized as having the facilities described in the preceding paragraph and that requires the suitability for installation in accordance with the code. So you have a panel board, it's listed It has an overcurrent device inside, feeding a surge product device inside. The overcurrent device is not accessible through the dead front. That is permitted. Why is that permitted? A, it's listed equipment, and B, that circuit that is within the enclosure is not a branch circuit. I was thinking it was a branch circuit, but it's not, because it does not leave the enclosure. It's internal wiring to the enclosure. So it does not, that overcurrent device is not required to be accessible or readily accessible through the dead front. It's just like an industrial control panel. I can have an industrial control panel. I can have little, I can have circuit breakers inside. I can have little switches inside. I don't have to put those through the dead front. Why is that? Well, it's an industrial control panel, and there's all part of what's inside. And it's a listed piece of equipment assembly, UL 508 listed in assembly. That panel board that has surge inside and the overcurrent protective device inside does not have, that overcurrent device does not have to be accessible externally through the dead front. It can be internal. So that's all I have to say about that. Now, you might point out 240.24, but you know, it's a listed piece of equipment based on 90. Whatever I just read. You don't inspect inside of listed equipment unless you detect something has been modified or changed. So, all right. So Q&A Friday has come to an end, my friends. I only got through 3 questions. Dan Marino, I will look into some of the things that I did for my PE exam. I by the sense of it, you're probably going to be taking the way they do the PE these days. I think it just focuses on power systems engineering. You don't have to worry about like Boolean logic and all this other good stuff. So, hey, Susan. Yes. Adverse weather post-closure. I'm telling you, it is really, it's really something outside. It snowed outside. I got to go see if it snowed anymore. I might have to go get my snowblower out. So unless I can't remember who it was up above, I think, I don't know if it was Willie Snyder. I don't know if it was you or Michael Savage. Somebody said they were going to come to the house and shovel off all the sidewalks and everything. So anyway. All right. Well, I really appreciate you. Thank you, Susan. Thanks, Dan. Thanks, Nihad, El Sharif, out there, and anybody else out there who is watching and listening on either YouTube, Facebook, LinkedIn, Instagram, and Twitter. I'm out there on Twitter too. Don't forget to subscribe. You know what to do. You hit that subscribe button, please. Hit the thumbs up. Smash that like button. And if you don't like it, if you want to hit the thumbs down, you got to hit it twice. So just to be sure, always hit that thumbs down twice. Hit the thumbs up only once. All right. That's all I have to say. Thank you, Lou. Thanks for joining. And I appreciate you. I appreciate Dan and everybody else. So hopefully we had a decent Q&A Friday. I will be back online again. We'll be talking code changes. So remember to subscribe to my YouTube channel, because if I go, like, for example, if I start working on it over the weekend, you know, if I come down here and say, hey, I'm gonna burn out an hour on code changes, I'm gonna hit that button and I'm gonna go live, but only on my YouTube channel, because I want to keep track of the dialogue. So, all right, thanks everybody. Have a great weekend and be safe. And remember, stay healthy. We need everybody around. Thanks, Nihad. I'm going to be taking a look at our paper this weekend. So I will be focusing some time on that, and I'm not going to do that live. All right. Thanks, everybody. Take care. Stay safe. And please stay healthy. Until we meet again online, or hopefully in person one day, I am signing off. Ta-ta for now.